So today I'm going to show how to run a simulation of a single pencil beam in water phantom on FRED. So what is FRED? FRED stands for fast particle therapy dose evaluator. I know the acronym doesn't match properly, but uh, yeah, F is for fast, R comes between the particle R, and E is in the therapy somewhere in the middle, and dose FRED, D for dose, and evaluator is I, I mean they could have done FRED D or something, but it's okay. Anyway, we'll do a simple example. This example you can find on FRED's documentation. They have done a really good job with the documentation. I'm just going to show you how to run it, and perhaps I'll explain along what does the code mean. And this is my understanding, and of course I can be wrong. So you have to write this in a text file, and I usually save it as fred.inp because when I run the program, if I write fred in the same folder, like in the terminal, I'll show you later on, it runs easily. But if I save the name as something else, for now I'm having difficulty, but maybe later on perhaps I'll find the way to run exactly. What I'm trying to say is, if I write fred inp here, save the file as fred inp, and when I will run the program with just fred, okay, I'll show you later on. So first we are defining the region. The region here means where my phantom is. So id is my phantom. Where is my origin? Of course I'll keep it at 0, 0 at the center. This is forward vector. This says along which direction the beam will go. I say it goes in the z direction. And where is the up vector? And I'll keep the up vector as in the y direction. So I hope you're what I'm trying to say is, the beam is in the z direction. That means the beam is coming like from my side to the screen and going beyond the screen. And let's say the screen is the phantom, and y is towards the camera of the laptop you're watching, or the phone you're watching on. That's the y direction, the up vector. This is completely what I have understood. I might be wrong, which I will correct it later on. And L stands for the length of our phantom. I will quickly type it in so that the video is not very long. Pivot here means, so the pivot 0.5, 0.5, 0. Pivot here stands for exact, if you 50% of the length. 0.5 is 50% of the length in x direction, and the second 0.5 is the 50% length in the y direction. And that is where we are pointing the beam will enter the phantom. It will start at the surface, at the monitor, at the screen which we are looking at, and which is 0 at z value 0. And at the center we have the x and y as at 5 centimeter, you can assume, from below. At the center 0.5 means 50% of the length in x or y. I might be confusing at first, but yeah, voxel I'm taking as a 1 millimeter 1 voxel. So the length of the cube here is 10 centimeter, 10 centimeter, and 20 centimeter in z direction, y direction, and x direction. So 10 centimeter is 10 100 millimeters. So when you divide 100 by 100, you get one voxel, 1 millimeter voxel in x direction, 1 millimeter voxel in um, y direction, and 200 millimeter divided by 200 is 1 millimeter voxel in z direction. Of course, I'm going to um, simulate this in water. Now I'm going to write for the beam parameters. So again, beam is a field. I give this, you always have to, you can write it other way, but I'll keep it simple. I have to give an ID, so that when in later on there are multiple beamlets, then we can use field 1, field 2. So yeah, FRED. I did not tell you about much about FRED. So FRED is a Monte Carlo engine which simulates um, how those are deposited by proton or ions in a material accurately and computationally quite fast. So what I have seen for simple water case, simple water phantom, it's at least 8 times faster than the MC square code or MC square Monte Carlo code, and also quite accurate. I will discuss those things later on as well. This says where does my beam starts in the uh, I mean, where is the nozzle? So I'm saying my nozzle is towards me, like minus 40 centimeters. I'm looking at my phantom from minus 40 centimeters, and it will shoot the beam, and it will go through the monitor, that which is our phantom, which is at 0 0, and then the monitor extends, the phantom extends to 200 millimeters or 20 centimeters in z direction. Again, this yeah, I have to. So this code has to also tell the algorithm, I mean, we have to tell the algorithm that the beam is of same length as that of um, the phantom, because it takes in the beam matrix in the form of 3D array. So we have to define a length. If we go less than the length, it throws an error. Again, still it's unclear to me, but I will later on find it out. And this pivot tells where exactly the beam starts. So for example, it starts at the center of the phantom in x and y direction, but I want it also be, I don't want it, from the example what I understood is it has to be they are putting it at least 20%. They're starting to simulate the particles when the particle is 20% inside the phantom. That is what I understood. We can check by changing it to 0 and starting at the very beginning. But for first, let's just yeah, that's our pencil beam. How is that different from the beam here? I think the field defines the matrix through which the pencil beam would come. A lot of pencil beams, field 1, field 2, and you define each pencil beam, you give energy to each pencil beam here. So this pencil beam corresponds to this field, which will emerge at this point minus 40 centimeters before the phantom is embedded in this matrix of 10 centimeter, 10 centimeter, and 20 centimeter of uh, the it looks like a phantom matrix from where the beam will emerge, but it's because of the coding, I guess. and this says that it will center and 20% inside of the Z. And this is the pencil beam whose energy we will define now. Also we have to call field ID 1, maybe because perhaps later on we can use this to connect it to another pencil beam. It reminds me of primary key and foreign key in Excel. Our particle is proton, of course. Mean, yeah, let's be it. It's in 150 MeV. From the documentation, I have learned that the units of energy is MeV when you give it here. So EFWHM is, so in reality, when you send in the protons for the treatment or to the phantom, it's not monoenergetic. There is always spread of energy, and here we can control the spread of energy by EFWHM, energy full width half maxima. So we have they have taken the Gaussian distribution, and because it's not monoenergetic, we go for the real case. And now we will discuss the how our proton is coming out of the accelerator, the nozzle. So when proton comes out of the accelerator, they have this divergence. We can converge or diverge the protons. They can yeah, we can, there is this parameter where it can diverge, and which is given by alpha factor. 2 is alpha factor, which says it can either converge or diverge. Let's keep it like that, 590. I'm looking up this number from the example. 2 is beta x. So the beta is how the beam is, I think it's the radius. Let me check. Sorry for this. Yeah, so when proton comes out, I mean the group of number of protons come out, it comes out in a radius. So alpha says how our beam is beam are converging or diverging. Beta says what's the radius of the beam, and the product of not the product, the emittance which I'm going to write now. Yeah, the beta is the size. So beta can't be 0, so we have to give some value. Alpha can be 0, but beta can't be 0, so we can give like 0.001. Let's simulate a pencil beam with very thin pencil beam without any spot, like spot size equal to 0 or almost 0. Emittance tells us about how how divergence, is it diverging or converging. The eclipse, emittance represents the eclipse of the proton beam that is coming out of the accelerator. I can keep it as 0 so that it simulates as a very thin pencil beam. And we will keep this is the plane where the protons are emerging. PB, yeah, that was our. and we will simulate 1 million particles. Hope it runs. So yeah, now about the FRED INP that I was talking about, it will be clear now. But first, yeah, I'm in my example clear. So yeah, if I write FRED right now and just press enter, my simulation should run, because the name I've saved it as FRED.inp. But if I would have saved it as another name, let's say uh, pencil beam .inp, and if I would have written FRED to run it, it throws error then. That is what I was trying to tell then, but hope so it doesn't throw error now. It did. Okay, where does it say -40 here? Yeah, I know. Not again. PB1 is too close to the boundary of field 1. Is it? What did I do wrong? Fill pivot PB1. It has to do with something with this. I mean, that's all right. Field 1 particle proton. Yeah. Twist alpha x. I've taken random, I mean not random value from the example. Why that could be? Emittance, reference plane, distance 40, number of pencil beam, fill pivot. Did I miss any? I can't see where the error might be coming from. Yeah, pivot is alright, materials and stuff. You can also write the field like this in this format by giving greater than, less than symbol. It started simulating though. Radius. We have to give it some radius, maybe more than one. I mean, not more than one. I mean, that was maybe too less, but I did it with zeros sometimes before. I knew that's not the problem. Okay, what if I do just copy paste? Okay, I'm gonna copy paste the values here. Save. So it ran because 10 to the we are simulating for 1 million particles, so it was very fast. Yeah, 3 seconds. Now if we change the radius to 0.01, okay, let's see. There, okay, wait, hold on. Whoa. So I have the emittance means that the eclipse size is 0. I mean spot size is 0 completely, but there is radius and it's converging beam because of minus. Well, let's see how the results. Let's plot this. I have Python code for that. Let's run that. Yes. So this plot is from previous part, but when I ran the program, it saved the .mhd file at this location. So I have made it. I have written the code in such a way that the latest file gets run. So if I run, I hope it doesn't throw error and shows me what my plot looks like. Yeah, it's a very thin pencil beam. There you go. There's our Bragg peak. The dose gets deposited. So it's with no spot size. Yeah, here comes our the proton beam. I mean, it enters here at exactly here with no spot size, and it goes, and it deposits the dose at around maybe 165 millimeters, and then it disappears. The energy disappears, and we get the Bragg peak at around 153 millimeters. So we can be very precise with the millimeters if we, where is it, if we change the voxel size, we can be more precise with the, let's see, let's make voxel size as 0.5, 200, 200, 400. Let's run this and see what happens. I hope the video is not too long. Well, the time increased. That means because the number of voxels that it has to compute, the dose in, that's why it took more time. How am I making this integrated depth dose plot is by I take all the xy plane, I take what energy was deposited in the first slice, first xy slice, xy plane, second one, third one, and then I add it up and then I plot it. Yeah, it's a good one. Well, our voxel has increased, but how can I increase my precision by making the voxel 0.5, and but I'm not able to get quite precise here. It says in millimeters. Nothing changed. What happens if I make this make my voxel quite large? Let's see. Let's see. So, mm, oh, I'm making my voxel very small. I want to make it large. Now my one, so 100 millimeters divided by 10 millimeters or 10 is, so one voxel is of 10 millimeters. Let's just see what happens. And the code should run faster this time because the number of voxels has gone down. And it is taking more time, which is quite surprising. Or maybe it is about to throw an error. Whoa, I have no clue why that could be. I have increased the number of, that means the number of voxels that it has to do the computation for has gone down. And still it took a longer time. Nothing is changing here. Maybe it's because, oh, there is no change in the, I'll look it later on and come back with another video. So that was how that is a simple example of FRED pencil beam in a water phantom. Yeah.